which is a value that serves as a unique identifier for an external visitor. It is defined as the int data type. The other parameter is named exit date time, and as the name suggests, this parameter denotes the date and time when an external visitor exits the building. So firstly, let's write code to find the external visitor within the underscore external visitors list. If the external visitor is not null, i.e. the external visitor is found within the underscore external visitors list, let's write code to update the relevant external visitor object's exit date time property to the date and time when the external visitor exited the building. Let's then write code to traverse the underscore observers list and call each observer's onNext method, and pass an argument to the onNext method of the relevant external visitor object to notify the observers that a specific external visitor has exited the building. So let's create another public method that will be called when the cutoff time is reached. So by cutoff time, I mean this is a time after which external visitors are not allowed to enter the building. So we need to use our imaginations for some of these methods because we are basically saying that this method is called when certain conditions are met. In this case, when a certain time in the day is reached. Just like, for example, when the external visitor enters the building, the confirm external visitor enters building method is invoked, or when the external visitor exits the building, the confirm external visitor exits building method is invoked. So let's create a public method that will be executed when the visitor cutoff time is reached. Let's name this method building entry cutoff time reached. So this method is called at a particular time, but we only want to call each observer's onCompleted method if all external visitors have left the building. The fact that the onCompleted method is called means that no further notifications will be sent from the observable object to the observer objects for a particular day. So we are going to use the link technology to check if any external visitor objects exist within the underscore external visitors list. But first I'm going to extend the external visitor class to include a property named inBuilding. This property is of type Boolean, and we can set this property according to the external visitor's current location. So we want to set the inBuilding property value to true when the confirm external visitor enters building method is invoked. Conversely, we want to set the inBuilding property value to false when the confirm external visitor exits building method is invoked. So we can now use the inBuilding property value to check if there are still external visitors left inside the building after the cutoff time has been reached. If you don't fully understand this code, don't worry, Link will be discussed in detail in upcoming tutorials as part of this C# advanced course. If the count of external visitor objects within the underscore external visitors list that have their inBuilding property value set to true is equal to 0, this means that the cutoff time has been reached and all external visitors have exited the building, so we can now call the onCompleted method on all the observer objects that are currently in our underscore observers list. By calling the onCompleted method on these observer objects, this is notifying the relevant observers that no further notifications will be sent. Okay, let's implement the subscribe method. So notice that the subscribe method contains a parameter of type iObservable, which is a generic interface. The implementation of the iObservable generic interface in this class, i.e. the Security Surveillance Hub class, is strongly typed with the external visitor user-defined type. So this is automatically propagated through to the subscribe method definition, where the iObserver generic interface is also strongly typed with the external visitor user-defined type. Note that when an observer object subscribes to the observable object, the observer object passes a reference to itself into the subscribe method. The this keyword can be used for the purpose of referencing an object derived from the class in which the this keyword is implemented. We'll implement this code when we create the observer classes in a bit. For now, let's implement the code for the subscribe method. And the code for this method is pretty simple. We first check if the observer object exists within the _observers collection. If the observer object does not exist within the _observers list, this means that a new observer object is subscribing. So we can write code here to add the observer object to the _observers list, which means that the relevant observer is now subscribed. The subsequent lines of code traverse all the external visitor objects within the _external visitors list and notifies the new observer object of the current information related to external visitors that exist within the _external visitors list. Now notice that the subscribe method returns a type that must implement the built-in iDisposable interface. So we are now going to create a class named unsubscriber, and this class will implement the iDisposable interface. As the name suggests, the purpose of the unsubscriber class is to provide a facility for the observer objects to unsubscribe to the observable object, i.e. to elect to no longer receive notifications from the relevant observable object. The unsubscriber class implements the built-in iDisposable interface, which contains a definition for a method named dispose. When an observer object calls the dispose method, this action causes the relevant observer object to unsubscribe from the relevant observable object. So you can see that the subscribe method in the observable class, in this case the observable class is the class named Security Surveillance Hub, allows for an observer object to subscribe to the relevant observable object. The subscribe method returns a reference to the relevant unsubscriber object, which is derived from the class that we're about to create, i.e. the unsubscriber class that implements the iDisposable interface. The observer object can simply call the dispose method, which is a member of the iDisposable interface, to unsubscribe to the relevant observable object. The built-in iDisposable interface is a member of the system namespace. Let's create the unsubscriber class. As mentioned, the unsubscriber class implements the iDisposable interface, which contains a method definition for a method named dispose. So let's create the class definition for the unsubscriber class. Let's indicate that we wish to implement the iDisposable interface. Let's ensure that we are implementing all the members of the iDisposable interface. The iDisposable interface contains one member, a method named dispose. Let's create the constructor. You can see that this constructor contains two parameters. The first parameter is a list that contains observer objects. The second parameter is an observer object. So the functionality for this class is literally just to remove the passed-in observer object from the relevant observers list. So let's create two member variables. These member variables will be appropriately assigned the passed-in arguments to the constructor. Then the logic within the dispose method is simply to check if the relevant observer object exists within the relevant observers list. If it does, remove the relevant observer object from the observers list. The result of this action is that the relevant observer is unsubscribed from the relevant observable object and will therefore no longer receive notifications from the observable object. So let's go back to the subscribe method in the Security Surveillance Hub class, and let's return a new unsubscriber object derived from the user-defined type that we have just created. Note that the construction of the unsubscriber object entails passing a reference to the relevant observer and a list of all observers currently subscribed. Okay, so we have now written the code for the observable object. The class that defines the observable object is the Security Surveillance Hub class. So we can now create the classes that will represent our observer objects. We are going to create two classes which represent two types of observer objects. The first type we'll create is a class named Employee Notify. This class will represent an employee, a staff member that works in the building, that has been designated as the contact point for an external visitor. So this employee wants to know when the relevant external visitor has entered the building so that the employee can welcome the relevant external visitor at the entrance of the building. The second type or class will represent the security team, which must receive details of the external visitor when the external visitor enters the building and later exits the building. So let's first create code for the Employee Notify class. This class is an observer, so it must implement the generic iObserver interface. We also need to strongly type the iObserver generic interface with the external visitor type. So one way we can automatically generate the definitions for the members of the iObserver interface that we must implement is to hover our mouse pointers over the red squiggly line under the iObserver generic interface text within our class definition and click Show Potential Fixes and then click Implement Interface. And Visual Studio automatically generates default implementations for 3 methods. The method definitions for these 3 methods are members of the iObserver generic interface. The red squiggly line disappears because we now have implementations for the members contained in the iObserver generic interface. So in a bit, we'll implement more useful code for these methods. Before we create a constructor for this class, I want to create a definition for an employee record. Let's create an interface named iEmployee. We'll keep the employee record really simple. So let's create definitions for just 4 properties. ID as int, first name as string, last name as string, and job title as string. Let's create a class named Employee that implements the iEmployee interface. So let's go back to the Employee Notify class and create the constructor for this class. So when an object is created from the employee class, we want an employee object to be passed into the constructor of the Employee Notify class. So let's include a parameter of the iEmployee type within the constructor definition. We want to adhere to SOLID principles. The last letter in the SOLID acronym is Dependency Inversion Principle, which states that classes should not depend on concrete implementations, but should only depend on abstractions. This is why the parameter within this constructor is defined with an interface type rather than a class. So we are defining this parameter of type iEmployee rather than of type employee. Very basically, SOLID is an acronym representing a set of principles that are design principles that can be followed in order for a programmer to develop software that is easy to maintain and extend. We'll discuss SOLID principles in detail in upcoming tutorials. SOLID principles serve as a foundation for object-oriented design patterns, like, for example, the observer design pattern. These design patterns can be implemented to solve problems that have been repeatedly identified in real-world scenarios. If you wish to read more about SOLID principles, please navigate to this URL. So let's create an appropriate member variable of the iEmployee type, and within our constructor, let's assign the passed-in value to the member variable we have just created. So let's implement our code logic for our onNext method. Notice that the parameter contained within this method is of type external visitor. When we automatically generated our default method implementations through Visual Studio, the fact that we had strongly typed the iObserver interface with the external visitor user-defined type propagated through to the onNext method. So the purpose of the onNext method is that it gets called by the observable object every time it is appropriate to send out notifications to the relevant observers. This is how the observable object is able to send out notifications to each of its subscribed observer objects because the observable object knows that each observer object implements the onNext method. So the observable object traverses all of its observers and calls the onNext method on each of its observer objects to send out the relevant notifications. Each observer is able to handle the notification through its custom implementation of logic within its onNext method. So the code we are about to write gets called when the observable sends out its notifications. In this case, we want the designated employee contact to receive a notification when the relevant external visitor has gained access to the building. So let's write the logic for this method. Firstly, let's assign the passed-in argument of type external visitor to a local variable named external visitor. Let's create an if statement. The condition for the if statement checks the external visitor object's employee contact ID property value against the ID property value of the employee object reference that is passed into the constructor of this employee notify object. If these two values match, this means that the relevant employee is the registered point of contact for the external visitor referred to in this particular notification. So we want to maintain an up-to-date local list of external visitors for this employee notify observer object. So let's define a member variable named _external visitors as a generic list that can store external visitor objects. So let's write code to check if the external visitor object passed into the onNext method exists within the _external visitors list. We can do this by using link and checking if the ID of the external visitor object passed into the onNext method matches any of the external visitor object's ID properties currently stored within the _external visitors list. And we are assigning the result of the link expression to a local variable named external visitor list item. So let's write a nested if statement where the if condition checks if the external visitor list item variable value is null. If it is null, the external visitor object does not exist in our local list containing external visitor objects. So let's add this external visitor object to our list. Then the next line of code simply outputs a message to the relevant employee that the expected external visitor has entered the building, and we can also include the external visitor's details within the message. So if the else part of the nested if statement condition is true, the external visitor has already visited, and the notification must refer to the relevant external visitor exiting the building. So the logic simply updates the in-building property of the relevant external visitor object within the _external visitors list to false. The relevant external visitor list item's exit datetime property is also appropriately updated with the relevant exit datetime property stored in the external visitor object passed in from the observable object to the onNext method of this object. So we have now implemented the logic for the onNext method of the employee notify observer class. So in the interests of time, we are not going to bother implementing code for the onError method We'll simply retain the default implementation generated by Visual Studio in this example, but please note that this method provides a mechanism for observers to handle exceptions that may occur within the observable object. So now we must implement the logic for the onCompleted method. The purpose of this method is so that the observable object can notify the relevant observer objects when no further notifications need to be sent. In this example, there is a rule that the observer's onCompleted methods will be called from the observable object when a cutoff time is reached, for example, perhaps 6 p.m. on a workday, and all external visitors must have left the building. So a few external visitors may still be in the building past 6 p.m. For example, they may be in meetings that have gone on for longer than was first anticipated. The onCompleted method on all relevant observer objects will only be invoked from the observable object once all external visitors have left the building and the cutoff time has been reached. Let's say the cutoff time means that no further external visitors are allowed to gain entry into the building on a particular workday after a predefined cutoff time. So, if these conditions are met, the observable can notify all observers through the observer's implementation of their onCompleted methods, and this means that no further notifications will be sent. At this point, the relevant observer objects will have a complete list of external visitor objects that visited the building during the course of the day. The external visitor objects will contain relevant information like, for example, certain details about the external visitors, as well as their entry and exit times to and from the building on the relevant day. So the observer at this point is able to create a final report relating to the external visitor data on a specific day. So let's implement the code for the onCompleted method in the employee notify class. Let's say that the relevant employee is only interested in the details of those external visitors that were there to visit the employee during the course of that day. So in the onNext method, we have only added the external visitors where the relevant employee was registered as the external visitor's contact in the building. So we can simply output the details of external visitors stored within the underscore external visitors list for the implementation of the onCompleted method. So let's first write an appropriate heading to the console screen. This heading will simply contain the employee name followed by the text Daily Visitors Report. Let's write code to traverse the underscore external visitors list. Let's set the in-building property to false, because if this method is being invoked, this means that all external visitors have left the building, and we want to keep our local copy of the underscore external visitors list up to date. Let's then write the details of each relevant external visitor to the console screen. This information serves as a final daily report for a specific employee and contains information about the external visitors that have visited the employee. So this is a report, and we want to space the columns for each of the outputted fields evenly. One way we can achieve this is by using the padWrite method, which is available on all string objects. The padWrite method accepts an integer value as an argument. So if, for example, we wish for the ID field to always occupy 6 character spaces, we can pass an argument of 6 to the padWrite method. So if, for example, the ID value only takes up 1 character space, the padWrite method will add the extra 5 character spaces, which will be empty spaces or white spaces, to the relevant field output. We can actually achieve the same effect when outputting variable values using an interpolated string, like this. So using the interpolated string technique, we can achieve the same thing and use less code. and that is the implementation for the onCompleted method of the employee notify class. So we also want to include a method that performs the action of subscribing to the observable. In this case, as we know, the observable is represented by the Surveillance System Hub class. So let's create a method named subscribe that contains a parameter named provider, which is of the generic interface type iObservable, and is strongly typed with the external visitor user-defined type. And to subscribe, we can simply write provider.subscribe and pass a reference to the current object using the this keyword to the observable's subscribe method. But remember that the observable's subscribe method returns an object that implements the iDisposable interface. So let's create a member variable of type iDisposable. Let's name this member variable _cancellation. So now we can create a method named unsubscribe. The logic to unsubscribe the observer is simply _cancellation.dispose. So as mentioned, we also want to implement code for another type of observer class. So the class we'll create for this will be named security notify. And as the name suggests, this class denotes the security team that must receive a notification every time an external visitor enters the building, and a notification when the external visitor later exits the building. So let's include the iObserver generic interface that is strongly typed with the external visitor user-defined type within our security notify class definition. Let's auto-generate the methods that we must implement for the iObserver generic interface. So let's hover our mouse pointers over the red squiggly line, click Show Potential Fixes, and then click Implement Interface. So the first method we need to implement is the onNext method. The logic here simply checks if the external visitor object already exists within the _external visitors list. If it doesn't exist, we add the external visitor object passed into the onNext method to the _external visitors list. We then output notification text that is appropriate for the security-related observer to the console screen. If the external visitor does already exist within the _external visitors list, this means the relevant external visitor has just exited the building, so we must update the relevant properties for this external visitor object list item appropriately. So we update the in-building Boolean property to false, and we also update the exit date time property with the date and time when the external visitor exited the building. And then let's update the code to output text to the security team that the relevant external visitor has now exited the building. And we have just written the onNext method. So let's implement the code for the onCompleted method. So within the onCompleted method, we simply want to output the details contained within the _external visitors list to the console screen, and this serves as a report to the relevant security team, conveying information about the entry and exit times of external visitors throughout the day. So we can simply copy the implementation for the onCompleted method within the employee notify class to the onCompleted method within the security notify class, and then manually change the heading to reflect that this is a daily report for the security team regarding external visitors. So let's finish off this class by implementing our subscribe and unsubscribe methods. So you may have noticed that we would actually be repeating the code for the subscribe and unsubscribe methods across our observer classes, namely the employee notify and security notify classes. So if we repeat the subscribe and unsubscribe implementations here, we are violating the principle of DRY, which is an acronym that stands for Don't Repeat Yourself. Here we would be clearly repeating ourselves. So let's refactor our code so that the subscribe and unsubscribe methods are reusable across our observer classes and are written in only one place. To centralize the functionality for these methods, let's create an abstract class named Observer. Let's make the Observer class implement the iObserver generic interface. Let's strongly type the interface with the external visitor class. So the rule here is that we must implement the members of the iObserver generic interface. In this case, however, we don't want to centralize the functionality for the onNext, onError, and onCompleted methods defined in the iObserver generic interface. We have different implementations for the onNext and onCompleted methods for our two different observer classes. So what we can do is we can create abstract method definitions for the relevant methods within our observer class. We can consolidate two member variables within this abstract class, i.e. the underscore cancellation member variable and the underscore external visitors member variable. The underscore cancellation member variable is of the iDisposable type and is used for unsubscribing an observer object. The underscore external visitors variable is of type generic list and is strongly typed with the external visitor type. The underscore visitors list maintains a central local storage facility for the relevant observer object of external visitor information. We can then centralize the functionality for the subscribe and unsubscribe methods so that these methods can be reused across both observer classes. As you may have guessed, the observer classes will inherit from this abstract class. So we can now change the class definitions for our observer classes, namely the employee notify class and the security notify class, to inherit from the observer abstract class. We then need to include the override keyword within the onNext, onError, and onCompleted methods within our employee notify and our security notify classes, which are of course classes that represent our observers. This is because we are no longer implementing the iObserver generic interface directly. We need to override the abstract method definitions for these methods that have been defined in the observer abstract class. So before we implement code in our main method and run the code, let's create a basic class that will help us differentiate between the text that will be outputted by our two observer classes, namely the employee notify class and the security notify class. So the obvious way that we can do this is by changing the color of the outputted text for each of these observer classes. So let's create a static class. Let's create a public enum and name it text output theme. Each list item value in this enum denotes an output theme. So let's name the first enum list item security. Let's name the second enum list item employee. Let's name the third enum list item normal. Let's add a method to the static class. Let's name this method change output theme. This method contains one parameter named TextOutputTheme and is defined as the enum we have just created, i.e. the enum named TextOutputTheme. Then the logic for the changeOutputTheme method simply evaluates through an if-else-if block the value passed into this method. So if the value passed into the changeOutputTheme method is the employee enum list item value, let's write code to change the background color to dark magenta and the color of the text to white. Else, if the value passed into the changeOutputTheme method is the security enum list item value, let's change the background color to dark blue and the color of the text to yellow. Else, let's reset the state of the text color and the background color back to their default colors. So let's go to the security notify class, and we can now change the color theme for the output text colors in the onNext method accordingly. And once the relevant text has been outputted, let's change the foreground and background colors back to their default values. And we can do this using our changeOutputTheme method, like this. Let's go to the employee notify class and implement the same functionality, but of course change the color theme to the appropriate color theme we have defined for the employee notify output text. So now when we test our code, we will be able to differentiate between the output coming from an object derived from the employee notify class and the output coming from an object derived from the security notify class. Okay, so let's write some code in the main method to test our implementation of the observer design pattern. We have implemented code here for the purpose of understanding the observer design pattern, and to keep things simple and focused on the observer design pattern itself, we have used the console app.NET Core project template to create the infrastructure or framework to house our code logic. So before we write calling code in the main method to test our observer design pattern, it may be helpful to use our imaginations to picture a real-world representation of this example. So in the real world, we would have three types of entities. We have our two types of observers, namely an employee who works within the building and the building's security team. So the relevant observer employees, i.e. the employees who have subscribed to receive notifications when an external visitor enters or exits the building, may have apps running on a handheld device like tablets or smartphones that alert the employees when relevant external visitors enter or exit the building. The security team may have various personnel whose responsibility it is to monitor the entry and exit of external visitors. So the relevant security personnel may be notified through security-related software where one of its components is subscribed to receive notifications when an external visitor enters or exits the building. So the relevant security officer or officers may be sitting at a laptop or desktop monitoring the relevant notifications. Then we have the observable entity, which could be a server that resides on premises or in the cloud, that is constantly receiving surveillance information from security cameras. It provides facial recognition functionality and assesses whether a registered external visitor can be authenticated and therefore enter the building. So in summary, the observers, i.e. employees within the building and a security team, are subscribed to the observable and receive notifications from the observable once a certain condition is met. In this case, the condition is an authenticated external visitor entering or exiting the building. With all this in mind, let's implement a few scenarios within our main method to test our implementation of the observer design pattern. So let's create an instance of our observable class. Let's create an instance of the observer class named employee notify and pass an employee object as an argument to the employee notify constructor. So we can imagine that Bob Jones is carrying a handheld device that receives a notification when an external visitor that has registered Bob Jones as the external visitor's point of contact arrives. Let's create another instance of the observer class employee notify and pass a new employee object as an argument to the employee notify constructor. So it's essentially the same scenario as before, but this time we can imagine that Dave Kendall is carrying a handheld device that receives a notification when an external visitor arrives that has registered Dave Kendall as the external visitor's point of contact. And these employees will also receive notifications once the relevant external visitor exits the building. Although they don't receive text output when the relevant external visitor exits the building, the notification is received and the relevant employee notify external visitors object list containing the relevant external visitor object is updated with relevant information, for example, the time the relevant external visitor exited the building. This information is relevant when the employee receives a report regarding external visitors, when the relevant cutoff time is reached, and all external visitors have exited the building. And let's create the other type of observer object, which is represented by the security notify class. This type represents a security team that must receive notifications whenever an external visitor enters the building and later exits the building. All observers will also receive a report once a cutoff time is reached and all external visitors have left the building. Remember, the cutoff time denotes a time after which no further external visitors are allowed to enter the building. So, for example, this cutoff time could be 6 p.m., which could be deemed as the end of the working day for the relevant company. So now we have 3 observer objects, which is comprised of 2 employees and the security team. And we have a provider, which can also be called the observable object, which is the central location where security-related data is processed. So let's subscribe all of our observer objects to receive notifications from the observable object. So when we call the subscribe method, we must also pass a reference to the observable object so we can call the confirm external visitor enters building method to simulate an external visitor entering the building. The arguments that we are passing to this method denote information about the external visitor, the time the external visitor enters the building, as well as the ID of the employee that serves as the contact point for the external visitor. So let's call the confirm external visitor enters building method to simulate the entry of an external visitor named Andrew Jackson and then an external visitor named Jane Davidson. Note that the last argument passed into the confirm external visitor enters building method denotes the ID of the employee whom the external visitors have registered as their point of contact. So the point of contact for Andrew Jackson is Bob Jones, and the point of contact for Jane Davidson is Dave Kendall. Let's then call a method to simulate these 2 external visitors exiting the building. We can do this by calling the confirm external visitor exits building method on the observable object. Once where the ID pertaining to the external visitor Andrew Jackson is passed into the method. We can then call the method again, but this time passing the ID of the external visitor Jane Davidson, signifying that Jane Davidson has exited the building. These 2 method calls to the confirm external visitor exits building method simulate these 2 external visitors exiting the building. So let's say that Andrew Jackson exited the building 2 hours after entering the building, and let's say that Jane Davidson exited the building 3 hours after entering the building. Lastly, let's call the building entry cutoff time reached method on the observable object, which denotes that the end of the working day has been reached. We have referred to this time as the cutoff time throughout this tutorial. If all external visitors have exited the building, a report of external visitors is sent out to all the subscribed observer objects. On a technical level, this is achieved through the observable object calling the onCompleted method on all relevant observer objects. We have structured the code in the main method so that all external visitors have left the building before the cutoff time, so a full report should be sent to all observers. And this also means that no further notifications will be sent for that particular day. So let's run the code. Okay, so an error is flagged because the underscore observers variable is null, and we have tried to call its contains method. So I've realized I forgot to include a constructor for the Security Surveillance Hub class, where we should have instantiated an appropriate generic list object and assigned it to the underscore observers member variable, as well as instantiate an appropriate generic list object and assign it to the underscore external visitors variable. So let's fix this issue and implement the appropriate constructor code for the Security Surveillance Hub class. Let's try again. Let's run the code. Great. And if we look at our output, we can see that this is an expected result. Bob Jones, an employee, is notified when Andrew Jackson, an external visitor, enters the building. Dave Kendall, an employee, is notified when Jane Davidson, an external visitor, enters the building. The security team is notified when both external visitors have entered and exited the building. When the cutoff time is reached, an appropriate report is sent to the employee observer objects as well as the security observer object. The employee report contains information regarding external visitors where the employee served as the relevant external visitor's point of contact. The security observer object is notified of the relevant activities and relevant details of all external visitors for the relevant day through a report tailored for the security team. Great, so our observer design pattern has been implemented correctly and is therefore working as expected. Though I've noticed that the date-time output is not in the format I would prefer. I want to include whether the time is AM or PM. So we can do this by including TT within the date-time formatting string passed to the relevant toString methods. This is not ideal because notice that we are having to change this format in several places. In a professionally developed application, it would be good practice to configure this format in one place. For the purposes of this demonstration, we'll update the date-time string formatting in several places, but let's be cognizant that this is not the best way to implement this formatting functionality. Let's run the code again. Great. So let's simulate the scenario where the cutoff time is reached. So no further external visitors are allowed to enter the building past the cutoff time. But there are still external visitors in the building. So we can simulate this scenario by commenting out the line of code that simulates the external visitor Jane Davidson exiting the building. So in this particular case, Jane Davidson has not yet exited the building. Let's run the code. And the output reflects this. We see the correct output pertaining to the entry and exit of Andrew Jackson, but we only see an output for Jane Davidson entering the building and not exiting the building. This is an expected result. Note that we also do not see any of the reports outputted to the observers because these reports are only sent when the cutoff time is reached and all external visitors have exited the building. The code implementation for this is implemented in the building entry cutoff time reached method, contained within the observable class, i.e. the Security Surveillance Hub class. In the building entry cutoff time reached method, the onCompleted methods of all relevant observer objects is called, but only if all external visitors have left the building. And if we include the method call to the confirm external visitor exits building method for Jane Davidson, but call the unsubscribe method on the employee notify object after this external visitor has entered the building, but before the building entry cutoff time reached method is called. So let's appropriately call the unsubscribe method on the observer object pertaining to the employee, Bob Jones. Let's run the code. And you can see that Bob receives a notification when his external visitor enters the building, but a report is not sent to Bob Jones when cutoff time is reached because he has unsubscribed before cutoff time is reached. This is because if an observer unsubscribes, the observer will not receive any further notifications after the observer has unsubscribed. On a technical level, when the observer unsubscribes, the code removes the observer from the observers list contained within the observable object, and therefore that observer is excluded from the list of observers that is traversed and sent notifications when certain predefined conditions are met. I hope you have enjoyed this video on the observer design pattern. This completes the final video in a video series on C# events and completes the fourth part of a course on advanced C#. So in this video series, we looked at the basics of events in C#. We demonstrated how we are able to subscribe to an event contained within another class, and how we can designate a method to handle the event. Event handling code in C# is implemented by using a delegate as an intermediary between the event and designated method that is called when the relevant event is raised. We demonstrated the use of raising events through code logic, i.e., when certain logical conditions are met in a class where the relevant event resides, the event can be raised in order to invoke the methods that have been designated to handle the relevant event. We demonstrated how when a calling client subscribes or unsubscribes to an event, that this functionality can be encapsulated within add and remove accesses, which are similar in nature to the use of get and set accesses for properties. We demonstrated how events can be raised through user actions, for example, a button click. We used the UWP Universal Windows Platform project framework as a foundation for this demonstration. We briefly touched on how the MVVM Model View View Model design pattern is used to loosely couple front-end functionality from business rules-related functionality when implementing code for a UWP project. In this regard, we also discussed the advantages of separating concerns, for example, to allow for cleaner code, to facilitate easier unit testing, to facilitate better maintainability of code, and to allow for separate teams to specialize in different aspects of a project, so relevant aspects of the project can evolve independently and without adversely affecting one another. Lastly, in this video, we demonstrated an example where the implementation of the observer design pattern was deemed as suitable because its core functionality involves pushing notifications out to multiple entities from a central point when certain conditions are met. Please consider subscribing for more content on advanced C# concepts like this and much more. And please ring the bell so that you can be notified when this channel releases new videos. If you feel you have gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. And please feel free to provide feedback about this video in the comments section. As always, the code can be downloaded from GitHub. A link to the relevant GitHub repository has been included below in the description. Hi, and welcome to the first part of a tutorial on C# generics. This tutorial is also the fifth part of a course on advanced C# topics. This video will serve as a basic introduction to generics in C#. We'll first answer the question, what is meant by generics? We'll look at a basic example of implementing generics in C# and the advantages associated with the use of generics in C#. So let's start with the question, what is meant by generics in relation to the C# programming language? Generics was introduced in C# version 2 and enables developers to use type parameters in code. This makes it possible to design classes and methods that defer the specification of one or more types until the class or method is declared and instantiated by client code. For example, by using a generic type parameter t, you can write a single class that other client code can use without incurring the cost or risk of runtime costs or boxing operations. We'll discuss what is meant by boxing operations and runtime casting a bit later in this video. Generic classes and methods combine reusability, type safety, and efficiency in a way that their non-generic counterparts cannot. Generics are most frequently used with collections and the methods that operate on them. For more content like this on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content released from this channel. Let's look at a simplistic example to help us understand generics in C#. To help us understand generics as a whole, we are going to look at a C# collection type, the array list, versus a C# generic collection type, a generic list. An array list provides the advantage of encapsulating the functionality of dynamically increasing the size of the list as more items are added to the array list. In other words, unlike with an array, we do not have to define an array list with a size. It will dynamically handle its size as items are added to the array list. The array list stores values as objects. This involves implicitly boxing value type items when they are added to the array list. Unboxing these items is required when these items are retrieved from the array list. We'll discuss boxing and unboxing in a bit. So we are only using an array list in this example to highlight the benefits that replacing an array list with a generic list provides. In doing so, we can understand the overall benefits provided through the use of generics. Note that Microsoft has stated that Microsoft does not recommend using the array list for future development. So we'll first use the array list collection in our example and later replace the array list collection with a generic list to highlight the benefits of generics. Let's create a console app .NET Core project. I'm going to name my project Generics Basics. Let's create a class named Salaries. Let's define a member variable as an array list. The array list type is a member of the system.collections namespace, so let's ensure that we include a directive to the system.collections namespace at the top of our code. And let's create a constructor. Within the constructor, let's populate our array list with data that denotes salaries. Let's create a public method named getSalaries that simply returns the array list that has been populated with the salary data. So this method returns an object of the array list type to the client code. So the code within our main method is our calling client code. The code here will create an instance of the salaries class and then call the getSalaries method and assign the returned collection from the getSalaries method to a local array list variable. So let's write the code in the main method to do this. Let's say there is a requirement to add a bonus of 2% to the second item within the collection. So let's write code to achieve this. We know that the salaries collection contains floating point numbers. So let's assume that we can assign a member of the collection to a local variable defined as float. So let's write the code for this. Okay, great. So this is good. We have a red squiggly line under the code where we are assigning the second item of the relevant array list to a variable we have defined as float. So a type incompatibility has been flagged by the C# compiler. If we hover our mouse pointers over the red squiggly line, we can see a message from the C# compiler which is telling us that we cannot implicitly cast an object to a float, but that an explicit conversion exists. So let's write code to explicitly convert the relevant object value stored in the relevant array list to the float data type like this. Great, and the red squiggly line goes away, and all seems well. Then we can finish off the code by writing code to write the salary, which now includes a bonus of 2%, to the console screen. Let's run the code. Oh, what is happening here? We have received a runtime error, specifically an invalid cast exception. The exception message states, unable to cast object of type system.double to system.single. Remember, float is an alias for system.single. So note that when we added the salaries to the array list within the constructor of the salaries class, we simply added literal values that are floating point values. We did not explicitly express the type of the relevant literal values. The type of floating point literals are by default interpreted as the double data type. We could have expressed the types for these literal values as float data types by adding an F after the relevant literal value, like this. But we did not do this. So in the main method, or in our client code, we assumed that a value within the array list was of the float data type, and this assumption resulted in a runtime error occurring. In a bit, we'll talk about how generics preemptively prevents such erroneous assumptions from causing runtime errors. Let's first discuss boxing and unboxing. Okay, so an array list stores values that are automatically typed as the root C# data type, which is the system.object data type. Note that all .NET data types ultimately inherit from the system.object data type. When a value type, in our case a numeric floating point value type, is stored within an array list, the value type is wrapped within an object type and stored in memory on the heap. This process is known as boxing. What does boxing mean? Boxing is the process of converting a value type to the type object or to any interface type implemented by this value type. So when the common language runtime boxes the value type, it wraps the value inside a system.object instance and stores it on the managed heap. For more information on data types in C#, please access a video created by this channel by clicking on a card made available in the top right-hand corner of your screen. A link to this video has also been included below in the description. So, when a value is retrieved from the array list, as we are doing in the main method, the value must first be unboxed. Unboxing extracts the value type from the object. Boxing is implicit. Unboxing is explicit. The concept of boxing and unboxing underlies the C# unified view of the type system in which a value of any type can be treated as an object. So this highlights two disadvantages of using an array list where a generic list can be used instead and can be implemented whereby the values contained within the generic list can be strongly typed through generics at compile time. Firstly, as we have proven, writing code in this way can result in runtime errors because the values in an array list are not strongly typed at compile time. Secondly, when a value type is stored within an array list, the value type is automatically boxed, and when a value type is retrieved from the array list, the value must be explicitly unboxed. This is done through explicit type casting. This boxing and unboxing functionality carries with it a performance overhead. Boxing and unboxing can affect the performance of our applications. Using a generic list to strongly type the values stored within the relevant generic list has two distinct advantages. One, type safety. The code is type checked at compile time, which preempts runtime errors. This makes typecasting at runtime not necessary, which eliminates the potential for type-related runtime errors occurring. Number two, enhanced performance. Unlike with an array list, the overhead of boxing is not necessary when adding a value to a strongly typed generic list, and the overhead of unboxing is not necessary when retrieving a value from the strongly typed generic list. Like an array list, a generic list carries the advantage of being able to grow dynamically, i.e., it is not necessary to define the size of the collection when it is declared. So with all that said, let's implement generics in our code. To implement generics, let's replace the array list within our salaries class with a strongly typed generic list. The generic list is part of the system.collections.generic namespace, so let's ensure that we have a directive to this namespace at the top of our code. Let's hover our mouse pointers over the list type in our code. So notice the T within angle brackets. This T serves as a placeholder for a data type. The developer is able to pass a data type as an argument to the generic list in order to declare that only the type passed into the T parameter must be stored within the relevant generic list. So we have passed in the float data type to our generic list. Notice how there is a red squiggly line under each of the floating point values we are attempting to add to our strongly typed generic list. The C# compiler is insisting that we express these floating point values as the float data type, and we know we can do this by adding an F to the end of each of these values like this. Through the use of generics, the C# compiler checks our code at compile time, which prevents the possibility of type-related runtime errors. So we are simply commenting out the code where we previously used the array list, and in its place, applying the relevant generic list code. Our list is now strongly typed with the float data type, which means that our list can only store value types that are of the float data type. This is the basics of generics. Let's run the code. Great! I hope you have enjoyed this video, which serves as an introduction to generics in C#. In the second video, we'll go further into generics and introduce associated concepts like, for example, constraints. For more videos on advanced C# concepts and much more, please consider subscribing, and please ring the bell so that you'll be notified of future content released from this channel. If you feel you've gained value from viewing this video, please hit the like button. It'll be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course welcome. The code created in this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Hi and welcome. This video is the second part of a video series on C# generics. This video is also the second part of the 5th tutorial in a course on advanced C# topics. So in this video, we'll create a class to encapsulate the bubble sort algorithm. This class will be a generic class that can be implemented to sort an array that contains values of any managed C# data type. This will include user-defined types. So in order to enable sorting user-defined types, the relevant user-defined type must implement the iComparable interface. The generic class that will implement the bubble sort algorithm will contain a constraint as part of its class definition. We'll discuss the significance of using constraints in the context of generics in C#, and we'll demonstrate the use of a constraint through the code example. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. Firstly, to highlight the advantage of using generics in C#, I'm going to implement the functionality for this example in a non-generic way. We'll then modify the code to implement generics to create the equivalent functionality. So let's get started. Let's create a .NET Core console application and let's name this project Generic Bubble Sort Application. I'm not going to explain the details of the bubble sort algorithm in this tutorial. There are many available online tutorials regarding the bubble sort algorithm. If you'd like me to explain the details of the bubble sort algorithm, please let me know in the comments section and I'll be happy to make a video on the details of how the bubble sort algorithm works. Very basically, the bubble sort algorithm is a simple sorting algorithm that repeatedly steps through a collection of values, compares adjacent elements, and swaps them if they are in the wrong order. Our implementation of the bubble sort algorithm will work for any array of any C# value type, string data type, as well as any user-defined type that implements the iComparable interface. So let's create a class that encapsulates a method containing the bubble sort algorithm. Let's first create this class as a non-generic class, so that we can later turn this class into a generic class, and in doing so highlight the benefits of using generics in our C# code. So let's create a public class named sortArray. Let's create a public method within the sortArray class named BubbleSort. This method does not return a value and contains a parameter which is an array defined as the system.object type. Remember, we are first implementing our code in a non-generic way. We want to be able to sort an array of any built-in value type, string type, and even user-defined types. We are using the object data type rather than generics to enable sorting arrays of varying data types. We are able to achieve this because all managed data types in C# ultimately inherit from the system.object data type. For value types, boxing functionality can be applied to store value type values inside an object reference type. For more information on boxing and unboxing, please click the card in the top right-hand corner of your screen to watch the first part of this tutorial on C# generics. A link to this video has also been included below in the description. So let's write the code for the BubbleSort method. Firstly, let's set a local variable of the integer data type to the length of the array that will be sorted by our BubbleSort code. This is the array that will be passed into this method at runtime. We are now going to create two for loops, an outer loop and an inner loop. Let's create the outer loop first. So this loop simply traverses all the elements of the array that will be passed into this method at runtime. For every traversal of the outer loop, the inner loop traverses all the elements of the array minus the current value of the outer loop's incremented value, in this case an integer value stored in a local variable named I. And of course we know that the -1 in both the outer and inner loops is there because arrays in C# are zero-based. So now, within the inner loop, we can write the code that compares the current element's value, i.e. the value currently being traversed, with the value of the adjacent element in the relevant array. So we can get the adjacent element by adding 1 to the value stored in the j variable, which is being incremented by the inner for loop statement. So notice the red squiggly line when we try to perform our comparison code using the greater than symbol. This is because the object type does not support the use of this operator for comparing one object value to another. So value types like, for example, int, float, long, etc., and the string data type implement the iComparable interface. So we should be able to use the compareTo method to perform the comparison functionality we need for our BubbleSort algorithm. The compareTo method definition is a member of the iComparable interface. The system.object type does not implement the iComparable interface, so we need to perform a runtime casting operation in order to use the compareTo method. This highlights the danger of using the object data type in code like this, because we are assuming that the elements of the array passed into this method at runtime will implement the iComparable interface. So this code runs the risk of causing a runtime error and at the very least carries the performance overhead incurred when the casting operation is performed at runtime. So we can perform the casting operation like this. The way the compareTo method works is that the current value is compared to another value. And if the current value is greater in value than the other value, an integer value greater than 0 is returned to the calling code. If the values are equal, an integer value of 0 is returned from the compareTo method to the calling code. If the current value is less than the other value that it is being compared to, the compareTo method returns an integer value less than 0 to the calling code. So with regards to the BubbleSort algorithm, if the compareTo method returns a value greater than 0, this means that the current value is greater than the value it is being compared to, and the two elements need to be swapped in terms of their positions in the array. So let's write the code for this. Let's set a variable named temp to the value of the current item being traversed. Let's then set the value for the current item in the array to the value of the adjacent item in the array, i.e. the value that the current item is being compared to. Then let's set the adjacent item's value in the array to the current item's value in the array, i.e. the value that is stored in the temp variable. So in effect, we have simply swapped the positions of two adjacent values in the relevant array. So in the interests of cleaner code, let's encapsulate this swapping functionality in a private method named swap. And that's it. We have implemented our bubble sort algorithm. So let's go to the main method and write code to test our sort array class. Let's create an array of integer values where the values are stored in no particular order. Let's write code to instantiate an object of the sort array type. Let's write code to invoke the bubble sort method and pass in the relevant array that we want sorted. Okay, there's a red squiggly line under the passed in array argument to the bubble sort method in our code. This is because we need to change our definition of the relevant integer array to an object array. Let's write the code to write the value stored in the relevant array to the console screen. Let's run the code. Great, and we can see that the values have been appropriately sorted. Let's test our bubble sort functionality for an array of strings. Let's run the code. Great. And let's now test our bubble sort code for an array of a particular user-defined type. Let's create our user-defined type. So let's create a class named employee. This will be the user-defined type that we'll use for this example where our bubble sort code sorts an array of a particular user-defined type. Let's keep this class simple and give it two auto-implemented properties, ID as int, name as string. Let's go to the main method and create an array of employee objects. I'm going to add made-up data for each employee object, and these employee objects are deliberately unordered. Let's run the code. And we are getting a runtime error. This is because our bubble sort code relies on the compare_to method to compare the relevant values in the relevant array. This means that the object stored within the relevant array must implement the iComparable interface. This highlights one of the reasons why our code should implement generics. We'll implement the generic version of this code in a bit. For now, to fix the runtime error, let's make the employee class implement the iComparable interface. Let's hover our mouse pointers over the red squiggly line under iComparable, click Show Potential Fixes, then let's click Implement Interface. We can now see that Visual Studio has created a method named compare_to. So we must implement code here that compares the current object's ID with the ID of the object passed into the compare_to method. So to get the current object, we can simply use the this keyword. The object that we'll compare our current object to is the object that will be passed into the parameter named obj, which is a parameter contained within the compareTo method. As you can see, the relevant parameter named obj is of type object, so we need to typecast this object to employee. Notice that we need to perform a lot of runtime casting to make this code work. This is not a good thing, and we'll solve this problem in a bit using generics. So, we are going to sort the employee objects in the relevant array by their ID properties. The ID property is of type integer. Integers in C# implement the compareTo method, so we can simply write code to return the result of the compareTo method to the calling code like this. So this code simply compares the ID of one employee object with the ID of another employee object and returns an appropriate value to the calling code. As stated earlier, a value greater than 0 if the current employee object's ID is greater than the other employee object's ID. 0 if they are equal in value, and a value less than 0 if the current employee object's ID is less than the employee object ID that the current employee object's ID is being compared to. The string data type also implements the iComparable interface, so we could replace this code with similar code that compares the current employee object's name property with the other employee object's name property. We'll test this a bit later. I'm also going to override the toString method in the employee class so that we can display the employee object's ID property followed by the employee object's name property when an employee item's values are written to the console screen. So when we write an employee item to the console screen, both the ID and the name properties of the relevant employee objects will be outputted to the screen. So let's run the code. Okay, so this is not the result we expected. In order for our override of the toString method to be executed, we need to typecast the item we are writing to the screen to the employee type. Note the need for more bad typecasting code. Let's try again. And now our code works as expected. You can see that the employee objects within the array have been ordered by their ID properties as expected. Great! So the sortArray class now works for multiple data types. We have achieved this functionality by using the system.object type. This is because all managed data types in C# ultimately inherit from the system.object type. For more information on C# data types, please click the card made available in the top right-hand corner of your screen to view a video on C# data types. So let's see how we can achieve the same functionality, but through the use of generics. We'll also see why it is more advantageous to use generics to avoid the performance penalties incurred by using the system.object type to achieve the desired functionality. So through our use of generics, we can also eliminate the risk of data type-related runtime errors. So let's change our sortArray class into a generic class. We can do this by adding a placeholder represented by a capital T within angle brackets after the sortArray class name in our class definition. Let's then replace all of our object type definitions with the placeholder data type represented by the capital T in our code. In the main method, we must add angle brackets after the sortArray type when we instantiate an object of type sortArray, like this. Within the angle brackets, we must include the relevant data type to strongly type the class. In this case, we are testing sorting an array of employee objects, so we must include the employee data type within angle brackets. We can now remove the casting operation from the code that writes the employee data to the console screen. Let's run the code. Great! We are using generics now, so let's remove the typecasting functionality where we are casting type object to type iComparable in the bubble sort method. Oh, but we now have a red squiggly line under the compareTo method call within the bubble sort method. The red squiggly line is a result of the fact that we have not told the C# compiler that type T implements the iComparable interface, which contains the compare_to method. So you'll notice when we add a dot after an item referenced in our array, the compare_to method is not available in the IntelliSense drop-down list. This is because Visual Studio and the C# compiler has no way of knowing that type T implements the iComparable interface. So, how can we declare that type T implements the iComparable interface? We can do this through the implementation of a constraint. By adding a constraint, we are constraining our T-type parameter to a rule that any type passed as an argument to the T parameter must implement the iComparable interface. So to add the desired constraint, we can add the following code to our sortArray class definition, where space T colon iComparable. So we have now implemented the desired constraint for our generic sortArray class, and the red squiggly line goes away. And now if we add a dot after our item referenced in the relevant array, we can see the compare_to method, which is a member of the iComparable interface in our IntelliSense drop-down list. So let's go to the main method. Let's first test our new generic version of the sortArray class that now contains a constraint with an array of integers. Now that we are using generics to implement the sortArray class, we can use the int type to declare our array of integers rather than the object type. So notice how we are passing in the int data type between the angle brackets for the code that instantiates the sortArray class. We are now able to strongly type our sortArray class. Let's test the code. Great! Let's test our string array, so this time we must include the string data type within angle brackets when we instantiate the sortArray class. Great! And then let's test our code with our array containing values of the user-defined type employee. But before we do this, you'll notice that we currently need to perform a conversion operation within the compare_to method of the employee class to convert the obj argument, which is defined as object, to an employee type. We don't want this extra overhead caused by the casting operation at runtime. So to solve this problem, we can implement the generic version of the iComparable interface. We can pass the employee data type as an argument to the generic version of the iComparable interface like this. So let's modify our code so that we are implementing the compare_to method contained within the generic version of the iComparable interface. To do this, let's first comment out our current compare_to method. Let's then hover our mouse pointers over the red squiggly line in our class definition. Click Show Potential Fixes and then click Implement Interface. You'll notice that the new version of the compare_to method generated by Visual Studio contains a parameter that is strongly typed with the employee user-defined type. So let's copy our old implementation of the compare_to method and paste it into our new version of the compare_to method. We can now remove the casting operation from our new strongly typed version of the compare_to method. So now there is a red squiggly line under the employee type being passed as a data type argument to the sortArray class in our main method. This is because in our sortArray class definition, we have a constraint which enforces a rule at compile time that any type passed into the sortArray class must implement the iComparable interface. Our employee class is now implementing the generic version of the iComparable interface. So we need to modify our constraint in our sortArray class definition to establish a rule that any data type passed to the relevant T data type parameter must implement the generic version of the iComparable interface. So, our constraint now pertains to any type that implements the generic iComparable interface. Following this modification, our code will still work for the integer data type, which is a value type, and the string data type, because both the int data type and the string data type implement the generic version of the iComparable interface. Our sortArray class will also work for any user-defined type, like our employee type, that appropriately implements the generic version of the iComparable interface. Let's test our code. Great! So let's say we want to sort our employee objects by name. To achieve this, we can simply change the implementation of the compareTo method within the employee class, like this. Let's test the code. Great! Let's also test the code for an integer array. Let's firstly select the int data type in our code, right-click on it, and then select Go to Definition. You can see the int data type implements the non-generic version of the iComparable interface and also implements the generic version of the iComparable interface. Let's run the code. Great! Let's also test the code for a string array. Great! So we have written a generic class that can sort an array of any built-in value type, string data type, as well as any user-defined type that appropriately implements the iComparable generic interface. By using generics, we eliminated the need for a lot of type conversion operations, which would be performed at runtime and carries the risk of incurring runtime errors. Using generics can also enhance the performance of your application because the .NET runtime no longer has the overhead of performing these casting operations at runtime. Generics allows us to defer type specifications for a unit of code. This allows us to strongly type a unit of code, for example, a class, method, or collection type, at compile time. This means generics inherently has the advantage of compile time data checks to prevent the possibility of type-related runtime errors occurring. We used a constraint to indicate to the compiler that the generic type parameter, represented by the capital T between angle brackets in our class definition, must implement the generic iComparable interface. This allowed Visual Studio to make available the compareTo method on an object defined as T through IntelliSense, and ensured that the compareTo method is available on all relevant elements within the relevant array, which are of type T, at runtime. So generics and the use of a constraint has been implemented so that we can implement one pattern of logic, in this case the bubble sort algorithm, for any C# built-in value type, e.g. int, long, float, double, etc., the string data type, as well as any user-defined type that appropriately implements the generic iComparable interface. I hope you've enjoyed this video on using generics with constraints in C#. In the next video, we'll delve deeper into generics. For more videos on advanced C# concepts and much more, please consider subscribing. And please ring the bell so that you'll be notified of future content released from this channel. If you feel you have gained value from viewing this video, please hit the like button. It will be greatly appreciated. Please feel free to share any of the videos released from this channel with anyone you feel may benefit from their content. Your comments are of course welcome. The code created for this tutorial can be downloaded from GitHub. Please see a link to the relevant repository below in the description. Hi and welcome. This video is the third part of a video series on C# generics. This video is also part of a tutorial which is the fifth part of a course on advanced C# concepts. In this video, we'll look at generic delegates and events in C#. We'll also look at other concepts associated with C# generics, including the use of a generic C# built-in data structure, namely the Q data structure. We'll explore these concepts associated with generics through a practical example. The theme I've chosen for this practical example is a warehouse management system. For more videos on advanced C# concepts and much more, please consider subscribing, And please ring the bell so that you'll be notified of future content released from this channel. We need to use our imaginations a bit because the example will be highly simplified and expressed through a .NET Core Console application. So the code will provide the functionality of a real-time monitoring system for items entering a warehouse and subsequently being processed. By processed, I mean the item is placed in a predefined location within the warehouse for storage. So an event is raised when an item enters the warehouse, and an event is subsequently raised once the relevant item has reached its predefined location within the warehouse. Note that when I refer to an item, I'm referring to a batch of units of a particular type. So in our example, the item can refer to a quantity of units. A unit in this example will be a hardware-related item. For example, a drill, hammer, ladder, etc. So if we use our imaginations, we can picture this scenario in the real world. An item enters the warehouse and is scanned. So let's say the item has a QR code attached to it that when scanned provides necessary information about the item. When the item is scanned, an event is raised. So for example, a supervisor could be monitoring the relevant activities relating to the warehouse, and when an event is raised, the relevant information is displayed on a screen in real time. So the supervisor could, for example, be monitoring these real-time events using a handheld device, a desktop computer or a notebook computer. The display could perhaps be a large screen TV that multiple employees can monitor. The use of events decouples the component that raises the event, which could, for example, be an on-site scanning facility, from the component that receives the event notification, which could, for example, be a handheld device used by a supervisor to monitor events either on-site or even remotely if required. So, for example, a box containing drills arrives to be stored at the warehouse. The QR code attached to the relevant box that the drills are in is scanned. The box is then transported to a predefined location in the warehouse to be stored. So when the box is placed in its relevant location, perhaps pressure pads at the location are used to detect that the box of drills has been processed. When I say processed, I mean has arrived at its designated location to be stored in the warehouse. So when the relevant pressure pad detects that the relevant box has been placed in its designated location in the warehouse, an event is raised. And the relevant information about the event is sent to the calling code, which will then display the relevant information about the event and the processed item to the supervisor's screen. So this is a real-time monitoring system for a warehouse. Please note, I've never actually worked in a warehouse, and this example is purely from my imagination. It's obviously always best when building a particular kind of application or system to consult with someone with the relevant domain knowledge. This example only serves to help with the understanding of generic delegates and events. Right, let's begin. Let's create a .NET Core Console application and let's name this project Hardware Warehouse Management System. So this project will contain our calling client code. We want this project to reference another component responsible for generic functionality associated with a warehouse. So let's add a .NET Standard Library project, and let's name this project Warehouse Management System API. Let's create a reference to the Warehouse Management System API project from the Hardware Warehouse Management System project. So we'll start by building the generic functionality for our Hardware Warehouse Management System by adding code to our Warehouse Management System API project. So we have separated concerns here. We have created two components, one to handle the specific functionality of the hardware warehouse. This functionality will be encapsulated in the Hardware Warehouse Management System project. The code in this component will focus on displaying the status and data about specific hardware-related items to a screen in real time as certain events are raised. The other component is a generic component specifically created for handling the management of any warehouse. This component is responsible for raising events associated with any warehouse to the calling client code. When each event is raised from the Warehouse Management System API component to the Hardware Warehouse Management System component, the relevant data associated with the relevant event and item is displayed to the screen in real time to, for example, a supervisor. So let's write the code for our example. Let's start by deleting the default class from our Warehouse Management System API project. Let's add a class named Custom Queue. In the Custom Queue class, we are going to wrap the functionality provided by the built-in C# generic queue data structure. We are going to customize the functionality of the queue by adding two events. Simply put, one event will be raised when an item is added to the queue. The other event will be raised when an item is removed from the queue. As you may have guessed, when an item is added to the queue, this denotes an item, for example, a box containing drills, entering the warehouse. The second event denotes the event that will be raised, for example, once the relevant box containing the drills has been processed, i.e., has been placed in its specified location to be stored within the warehouse. So let's make our custom queue class a generic class. A generic class can contain more than one type parameter, but we are only going to add one type parameter for this class. So using the capital T is the generally accepted way to represent the placeholder for a type parameter in a generic type definition. If there were two type parameters, we could add a comma and then the capital letter U to represent a second type parameter. This generic class will only contain one type parameter, so let's remove the second type parameter. So by adding T within angle brackets following our class's name, we have created our custom queue class as a generic class. So let's create a private member variable of the inbuilt C# queue generic collection type. So let's define this member variable as the generic queue data type, and let's name our variable _queue. And you can see that a directive at the top of our code already exists to the system.collections.generic namespace. The queue data type is a member of the system.collections.generic namespace. Let's create a parameterless constructor for the custom queue class. Let's instantiate the _queue variable within our constructor. Let's create a read-only property and implement code that returns the number of items currently stored in the _queue collection. Let's create the definitions for the public methods that will be included in the custom queue class. We'll first add their definitions and then implement the code for each method. Let's create a method named addItem that contains a parameter of type T. This method will be called when an item is added to the custom queue. Let's create a method named getItem. This method will return an item stored within the queue to the calling code. This method returns a value of type T and contains no parameters. Let's create a protected virtual method named onQueueChanged. This method will encapsulate the functionality for raising the events of this class. It contains a parameter of a user-defined type that we need to create. The value passed to this parameter will store information about the relevant event being raised from within this method. So let's create a class definition for a class named queueEventArgs. This class will extend the functionality of the system.eventArgs built-in class, so let's write code so that this class inherits from the system.eventArgs built-in class. Let's add a read-write auto-implemented property named message to the queueEventArgs class. The message property will return a string narrative which will include details about the item to which the event pertains, as well as information about the event itself. So the last method we need to create is a public method named getEnumerator. So this method returns a value of the generic IEnumerator interface type to the calling code. So let's implement the code for this method. The implementation is one line of code which returns the value returned from the _q member variable's getEnumerator method. By implementing this getEnumerator method on our custom queue class, this will allow the calling code to traverse the elements stored within the custom queue class collection using a for each loop. We'll demonstrate this at an appropriate time during the development of this example. So let's create our delegate type, which will be used to define an event in the custom queue class, i.e. the event that is raised when an item is added to the queue, and also an event raised when an item is returned from the queue. Let's define our generic delegate type directly within the Warehouse Management System API namespace. Let's create a public delegate named queueEventHandler that does not return a value and contains two generic parameters. The first parameter is of type T, and the second parameter is of type U. This is a generic delegate that contains two type parameters. So we must include the placeholder data types within angle brackets. The capital letter T represents a placeholder for the first generic data type parameter, and the capital letter U represents a placeholder for the second generic data type parameter. So now we can define the definition for the event contained within our custom queue user-defined type. So to do this, we use the event keyword. This is a public event to which we want our calling code to subscribe. So we precede the event keyword with the public access modifier. Then we follow the event keyword with the generic delegate type that we have just defined, the generic queueEventHandler delegate. And let's strongly type our generic delegate. Let's pass the custom queue generic user-defined type to the first generic data type parameter, and let's pass the queueEventArgs user-defined type to the second generic data type parameter. Let's name our event custom queue event. So let's implement the code for the onQueueChanged method. This method centralizes the code for raising the custom queue event. So the first argument passed to this event is of the generic user-defined type named custom queue, which is the class in which this method resides. So to get the current object, we can use the this keyword. The second argument is the argument passed to this method's parameter and will contain information about the event and is of type queueEventArgs. So we pass the onQueueChanged method's argument A as the second argument to the custom queue event. So let's implement the code for the addItem method. Firstly, let's write code to add the item passed into the addItem method to the _queue collection. Note that in order to add an item to the built-in C# queue data structure, we must use the enqueue method. So before we write the code to raise our custom queue event, which will be executed every time the relevant queue is changed, let's look at the queue generic collection type in C#. When we use the enqueue method to add an item to a queue data structure in C#, the underlying functionality of the queue collection type is adding the relevant item to the back of the queue, as it were. So later, when we write the functionality to retrieve an item from the queue, we'll use the dequeue method. The dequeue method retrieves an item from the front of the queue. The queue data structure works on a FIFO basis. FIFO is an acronym for first in, first out. So the item in the queue that was the first item to be added to the queue when the enqueue method was executed will be the first item to be retrieved from the queue when the dequeue method is executed. We'll use the dequeue method when we implement the functionality for the getItem method. Note that when the dequeue method is executed to retrieve an item from the queue, the first item added to the queue, which will be the item at the front of the queue, is removed from the queue, which means the item that was added to the queue right after the item that was just retrieved from the queue takes the position previously occupied by the item just retrieved from the queue. So the way the ordering of the queue data structure works is just like how a queue works in the real world. For example, consider people queuing to buy tickets to an event. When a person joins the queue, the person joins the queue at the back of the queue. The person at the front of the queue buys a ticket, then leaves the queue, making the person that was behind the person who has just left the queue now the person at the front of the queue. This person can now buy a ticket, and the cycle repeats. So after the enqueue method has been executed, this means the relevant queue has changed, so we want to raise an appropriate event to the calling client code to let the client code know that the relevant queue has changed. When the event is raised, we can pass two arguments to the calling client. The first argument is the queue itself, which is encapsulated in our custom queue generic class. The second argument contains information about the event as well as information about the item that triggered the event. This information is encapsulated in the queue event args user-defined type. So let's write code to instantiate an object of type queueVentArgs. And we want to send information about the item being added to the queue through the message property, which is a member of the queueVentArgs class, to the calling client code. Notice at the moment, if we include a full stop after the item variable, we don't get any properties in the IntelliSense drop-down list in Visual Studio. For example, we don't get the ID, name, or type properties that could provide useful information to the calling client code about the item that triggered the relevant event. So, how can we solve this problem? We can solve this problem by ensuring that items added to the queue implement a specific interface. Then we can add a constraint to our generic custom queue class that enforces a rule that type T must implement the relevant interface. So let's add an interface to our Warehouse Management System API project. Let's name this interface iEntityPrimaryProperties. Let's add three property definitions: ID as integer, name as string, and type as string. Let's go back to the custom queue class and let's add a constraint to our custom queue class. So we can add the constraint like this: where space t colon iEntityPrimaryProperties. So we now know that any item added to the queue will implement the iEntityPrimaryProperties interface, which means the item will have an ID property, a name property, and a type property. So because we have added this constraint, we should now be able to see these properties if we add a dot at the end of an object passed into the addItem method as an argument. So let's add a dot at the end of the item variable, and you can see the ID, name, and type properties in the IntelliSense drop-down list. This means we can include the information stored in these properties in our message to the calling client code. So in the message property, let's add a timestamp. So I'm going to add a new class named constants so that I can store a string constant that can be reused to represent a datetime format for this project. And let's include the formatting for the relevant date timestamp using our datetime format constant. Followed by the relevant ID, name, and type properties stored for the relevant item. Great, but let's say we want to include additional information in our message to the calling client code. We want to include the quantity of units that make up the item that has entered the warehouse. Remember, items are composed of units. We also want to include the value of each unit with the additional information. For design reasons, we don't want to include the quantity property and the unit value property in the iEntity Primary Properties interface. So let's add another interface to the Warehouse Management System API project, and let's name this interface iEntity Additional Properties. Let's add two properties to this interface: quantity as int, unit value as decimal. Let's go back to our custom queue class, and let's add another constraint to the custom queue class definition. To do this, we can simply add a comma and then iEntity Additional Properties to the custom queue class definition. Now let's see if our new properties appear in the IntelliSense dropdown when we add a dot after the item variable, which is of type T. And there you can see our additional properties, quantity and unit value. So let's include the quantity property in our message. The unit value property will be displayed to the user along with all the other properties in a tabular format every time the queue changes. We'll see this when we develop the calling client code. Let's add the following narrative text literal to the message property: has been added to the queue. So let's implement the code for the getItem method. So let's first assign the returned value from the relevant queue, i.e. the value returned from the dequeue method, to a local variable of type T. The dequeue method also removes the item at the front of the queue. So let's write the code that will notify the calling client that the queue has changed. Let's set the message property of the queueEventArgs object in much the same way as we did in the addItem method. The difference is that this method denotes that the relevant item in the queue has been processed, so let's reflect this in our narrative. So let's add the literal text has been processed to our narrative. So an item is removed from the queue once the item has been processed. By processed, we mean that the item has been placed in a designated location in the warehouse for storage. The item is added to the queue when it first enters the warehouse, then the item is scanned. When the item is scanned, the event in the addItem method is raised. When a predefined amount of items are in the queue, the items in the queue are processed, i.e., each item is placed in a specific location in the warehouse to be stored. Each time an item is placed in its location for storage, a pressure pad is activated at the relevant storage location, which raises an event to notify the calling client code that the relevant item has been processed. We have now implemented the code for the custom queue class, and we have also completed the code for the Warehouse Management System API component. Let's implement the code for the calling client. So in this example, we have a warehouse used for storing hardware-related items. When we refer to an item in the context of this example, we mean a collection of a certain type of hardware item. So for example, we are going to use 4 distinct item types: drill, hammer, ladder, and paintbrush. So in this example, an item could refer to a collection of drills, a collection of hammers, a collection of paintbrushes, or a collection of ladders. So let's define an abstract class named hardwareItem, which must implement the interfaces we created in the Warehouse Management System API component, namely the iEntity Primary Properties and the iEntity Additional Properties interfaces. We have already created a reference from the Hardware Warehouse Management System project to the Warehouse Management System API project, but we must also ensure that we have included a directive at the top of our code to the Warehouse Management System API namespace. So let's do this. Great. Let's create auto-implemented properties for each property definition in the iEntity Primary Properties and the iEntity Additional Properties interfaces. So let's create classes representing a specific type of item that will be stored in the warehouse. Let's start with the drill. So we must make the drill class inherit from the hardware item abstract class. Let's say we also wish to create more specific properties or behaviors for the drill class. We can do this by adding an interface to define specific properties or behaviors relating to the drill class by creating an interface that the drill class must implement. So let's create an interface named iDrill. For the sake of keeping our example simple, let's just add one property definition for the iDrill interface. Let's make it a string property and name it drill brand name. So this property is only intended to acknowledge that we are able to extend each of the classes representing specific products in this example, but we won't be using these properties further than this. So let's ensure that the drill class implements the iDrill interface. Let's implement the same design for our other items, ladder, paintbrush, and hammer. Great! So let's go to our main method and simulate items entering the warehouse by adding items to a custom queue object. Let's instantiate an object of the generic custom queue class defined in the Warehouse Management System API component that our calling client code references. Let's strongly type our queue with the hardware item abstract class. We do this because all items in our warehouse will inherit from the hardware item abstract class. So the next step is to wire up a method to handle the event defined within the custom queue class. This is an event that is raised whenever the relevant queue changes. For example, an item is added to the queue, denoting a hardware item entering the warehouse, or an item is removed from the queue, denoting that the item has been processed, i.e. the item has been moved to a predefined location within the warehouse for storage. So to wire up the relevant event, we type the object reference custom queue, add a dot, and then we can see the relevant event in the IntelliSense drop-down list. So let's select the event named custom queue event. Then we can type in the plus equals operator to establish a method that we want to execute when the relevant event is raised. So we can auto-generate the relevant method through Visual Studio by pressing the Tab key. We can now implement the custom code we want executed every time the queue changes within the relevant method we have just generated. So let's first write code to clear the screen. So notice that the first argument passed to this method is an object of type custom queue. It is named sender because the event that is fired resides in this class. So the event notification is sent from the custom queue class when the relevant event is fired. So the second argument is of type queue event args and encapsulates relevant information about the relevant event. So let's write code to check if the sender object, which is an object of type custom queue, contains any items. So to do this, we can use an if statement to check the queue length property of the custom queue class. So if the queue length property is greater than 0, let's write the properties of the items stored within the queue to the console screen. Let's create a private method named WriteValuesInQueue to screen that contains a parameter of type custom queue, which is strongly typed with the abstract class hardware item. Let's write a for each loop to traverse the items in the queue and write each item's properties to the console screen. So these items will be written to the screen in a tabular format, so I've made sure that each column is set to a specific length. Let's call this method from the custom queue underscore custom queue event method, i.e. the event handler method. So let's go to the main method, create 10 hardware items and add them to the custom queue. I'm actually going to change the name of the variable we are using to reference the custom queue object to a more specific name. Let's change the name of this variable from custom queue to hardware item queue. So I've already uploaded the code for this example to GitHub. In the interests of time, let's copy the code that adds hardware item objects to the relevant queue from the code I have already uploaded to a GitHub repository. So let's navigate to this web page from within our browsers and copy the relevant code and then appropriately paste this code into the main method. So this code, which adds hardware items to the custom queue, simulates items entering the warehouse. To give this example a more real-world feeling, to simulate that these items are entering the warehouse at random times, I'm using the system.threading.thread.sleep method to add a time delay between the lines of code that add items to the queue. So for example, here we are delaying the main thread for 2000 milliseconds, which equates to a 2-second delay. Let's go back to the custom queue underscore custom queue event method and add an else part to the top if statement. So if the queue does not contain any items, we want to output status information to the user. Let's output the following text to the user when the queue does not contain any items. Status: all items have been processed. So let's run the code. And you can see that each time an item is added to the queue, an event is raised and our calling client code writes the details of the item to the console screen. Great! So let's create the code for when items in the queue are processed. For the sake of keeping this example simple, let's say that when the queue contains 5 items, we want the items in the queue to be processed. So let's define a constant as an integer, and let's name this constant batch size. Let's set this constant to a value of 5. So we can now write a nested if statement in our custom queue underscore custom queue event method that checks if the queue has 5 items in it. If the queue has 5 items in it, we want code to execute that simulates the processing of each of the items in the queue. So let's write a private method named processItems. It contains one parameter of type custom queue that is strongly typed with the hardware item user-defined abstract type. Let's write code to simply traverse the items in the queue through the use of a while loop. The condition of the while loop is that iterations of the loop must continue while the queue is not empty. So we want to dequeue each of the items in the queue, meaning that the item has been processed. Remember that when the getItem method is called, the dequeue method on the underlying queue data structure is called, which means the item at the front of the queue is removed from the queue. Let's add a 3-second delay before each item is removed from the queue to simulate that the item is being processed. Let's